This is the third theory that we're going to look at, molecular orbital theory. And what this does is it calculates orbitals for the entire molecule instead of individual atoms. And of course, solving the Schrodinger equation, even for a really, really simple molecule, is impossible. So they start with a trial function as an educated guess, and then they basically iterate and move this way and that way until they find the one with the lowest energy. So that's our attempt to describe what nature is doing, but we can never do better than nature. So here what we're thinking about is what's known as a linear combination of atomic orbitals, LCAO, linear combination of atomic orbitals. And it's a weighted linear sum of valence atomic orbitals of all the atoms in the molecule. So it combines all the atoms, not just the central atom, not just two at a time, just all of them. So you have to combine all of them. And as a result of this, many of these types of orbitals are going to be delocalized. They're going to be spread out over the whole molecule instead of on a single atom, like the hybrid orbitals. So let's think about the simplest possible molecule, H2. So a hydrogen has one electron in the 1s orbital, and this guy has one electron in the 1s orbital. So these are going to have equal weights, and we're going to add them together. So we can add them together in phase, and we'll get something that looks like this. And that's going to have a lower energy than the original orbitals did. And this is called a sigma orbital because of the shape. If you imagine looking at the end of this, it would look round, like a sausage, right? Round, like the symbol sigma. And this is considered a bonding orbital because it's lower in energy than the original orbitals. So that's called a sigma 1s because the shape is sigma and it's made from 1s orbitals. The next molecular orbital is where we sum the two 1s orbitals when they are out of phase. So you can think of this as adding them together when they're out of phase. It's the same as subtracting, right? So if this one is out of phase with that one, and we add them together, we're going to get negative, destructive interference. And so we're going to get something that looks like this, where there's a big old node in the middle, and this is higher in energy than the original ones. So this is considered an anti-bonding orbital because it's not going to help the cause. So this is a sigma star 1s. So to recap, when we add these two orbitals together with destructive interference, we get something that looks like this, and it's got a node in the middle where there's zero electron density. That's not going to help those two atoms stay together. If we add them when they're in phase, constructive interference, they reinforce each other, and now we get a lot of electron density between. So this is a bonding orbital, and that's an anti-bonding orbital. If you start with two orbitals, you end up with two orbitals. Any questions yet? This is even weirder, isn't it? This is like really weird. So we can make a diagram called a molecular orbital diagram. So here is the orbital diagram for just a regular hydrogen atom. So 1s orbital with one electron in it. And over here's the other hydrogen atom, 1s with an electron in it. And when we combine these, we get one bonding orbital and one antibonding orbital. The bonding orbital is lower in energy, the antibonding is higher in energy. Notice here we're not drawing shapes, we're just using little boxes, okay? So these are the atomic orbitals, and that guy got drawn upside down just because we know he's going to flip when he gets into this orbital to pair up. So we have a total of 2 electrons, and so we put the electrons into this molecular orbital diagram the same way we've done other diagrams. Lowest energy first. They're going to pair up with opposite spins and until they move on to the higher energy orbital. So here what we see is that when 2 hydrogen atoms make a bond, the energy is lowered. And that's why hydrogen likes to form bonds. That's why hydrogen is naturally found as a diatomic element. We can talk about the bond order as being the number of electrons in bonding orbitals minus the number in antibonding orbitals divided by 2. So it's kind of a weird average. So here we're going to look at this molecular orbital diagram, and we've got 2 electrons in the bonding orbitals, and we have none in the antibonding. So 2 bonding, 0 non-bonding, divide that by 2, and that comes out to 1. So this has a bond order of 1. A positive bond order, even if it's like 1/2, is a good thing. It means that a bond will form. If the bond order is 0 or a negative number, the bond will not form. The larger the bond order, the stronger the bond. Okay, so let's look at helium. Helium has 2 electrons in its 1s orbital, but still it just has this 1s orbitals that have any electrons in them. So when we combine these 1s orbitals, we get a bonding orbital that's lower in energy and an anti-bonding orbital that's higher in energy. Now we have a total of 4 electrons to put into this diagram. We're going to start down here, 1, 2, and then go up here, 3, and 4. If we calculate the bond order, there are 2 electrons in the bonding orbitals, and there are 2 electrons in the anti-bonding orbitals. And we divide by 2, because it's kind of like an average, and we end up with 0. Which predicts that this is not going to happen, and it doesn't. There's no such thing as an He2 molecule. Any questions? What if we have an He2 plus ion? The molecular orbital diagram here is the same, right? Because we're still talking about 2 1s orbitals. And when they combine, they make one bonding and one anti-bonding. But because this has a positive charge, that means it's lost an electron. So one of these has 2 electrons, and the other only has 1, total of 3 electrons. So when we put those in here, 1, 2, 3, now the bonding order, there's 2 bonding orbitals, 2 electrons in the bonding orbitals, and 1 in the anti-bonding orbital, 2 minus 1, divided by 2. And so here, the bond order is 1/2, which is greater than 0. And so this does exist. It's not common, but it does exist. Questions?
So there will always be an anti-bonding?
Yes, whenever you combine 2 orbitals, you'll get 2 orbitals. 1 bonding, lower in energy, and 1 anti-bonding. Yep. So, again, we're not gaining or losing any orbitals. The number of molecular orbitals that you form is the same as the number of atomic orbitals that you started out with. When 2 atomic orbitals combine, you get 2 molecular orbitals. One's lower in energy, the bonding. One's higher in energy, the anti-bonding. When we put electrons in there, we're going to fill the lowest energy molecular orbitals first. with up to 2 spin-paired electrons will follow Hund's rule if we have orbitals of the same energy. So it's the same rules for filling the diagram. Stable bonds require a positive bond order. And a positive bond order just means you have more electrons in bonding orbitals than in antibonding orbitals. Because the bonding orbitals are fighting for a bond and the anti-ones are fighting against it. And so who's going to win? It's the one with more electrons. So use molecular orbital theory to predict the bond order in H2+. Is the H2+ bond stronger or weaker than the H2 bond? So here I have hydrogen, and here I have another hydrogen. One of these is going to have to be positive. So this guy has 1 electron, and this guy has no electrons. A little disturbing, but we'll just hang on. If I combine 2 atomic orbitals, I get 2 molecular orbitals. One is lower in energy, and one is higher in energy. This is called sigma 1s, and this is called sigma star 1s. So I look at my atomic orbitals, and there's how many electrons do I have? Well, I only have 1. So I have 1 electron to put in the middle here, in the molecular orbitals. Well, it's going to go in the bottom, right? This is atomic orbital, molecular orbitals, atomic orbitals. I am not going to make you draw any orbital diagrams. There will be at least one question about this on the next exam, but I will give you the diagram so that you can fill it in, just put the electrons in there, and answer questions, okay? So what is the bond order for this guy? Well, how many electrons are in bonding orbitals? 1. How many electrons are in non-bonding orbitals? 0. And divide by 2. So this gives me a bond order of 1/2. The bond order for H2 was 1. This is 1/2. Is it weaker or stronger? It's weaker. Questions? So these are homonuclear diatomic molecules. So diatomic, we're looking at molecules that have 2 atoms. Homonuclear means they are the same element. So the next set we can look at is like lithium-2, Li2. You might say, well, that shouldn't happen because lithium's a metal. Well, yeah, it is, but there's some weird things that do exist out there. So now we're the 2s orbitals. And again, we're just going to look at the valence electrons. And here, 2s orbital from this one. And again, you make one that's lower in energy, one that's higher. One that's bonding, one that's anti-bonding. So this is called sigma 2s and sigma star 2s. So we have 1 electron from each of these. Now why they didn't write that one upside down, I have no idea. But we have 2 electrons, we put the 2 electrons in here, and we get that. So the bond order would be, I have 2 electrons in bonding orbitals, and how many in the anti-bonding? 0. And I'm going to take that and divide it by 2, and that gives me a bond order of 1. This actually does exist in the gas phase. Let's look at Be2. we're going to use the same orbital diagram here because we're talking about 2s. So here beryllium has 2 electrons and this beryllium has 2 electrons, and so when we put these 4 electrons in, we're going to end up with 2 in the bonding and 2 in the anti-bonding. You calculate the bond order. We've got 2 bonding minus 2 anti-bonding, that's 0. Bond order is 0. This should not be stable, and it isn't. That was the s orbitals. Now I get to do the p orbitals. So first we're going to look at the px orbitals. So these are the ones that are along the x-axis. When we add these two together, one lobe is a positive phase and one lobe is a negative phase. And so we can add these together so that they are in phase, and then we get something like this where we get a big bulge in the middle and smaller bulges on the outside. Or we can add them when they're out of phase, and then we get little bulges in the middle and bigger bulges on the outside, but again we end up with this big old gap in there. This is an anti-bonding orbital. This is also a sigma orbital because just like the sigma bond, it's that end-to-end business, right? The other two orbitals are perpendicular, or, well, yeah, actually those are perpendicular to each other. So again, they have phases, positive phase and a negative phase, and so we can add them in phase and get something that looks like this, and we can add them out of phase and get something that looks like that. So this is called a pi orbital, molecular orbital, because it's kind of shaped like the letter pi. I don't think that's why they called it that, but hey, helps me remember it. So we get one that's lower in energy and one that's higher in energy. So this is pi star 2p and just pi 2p. So we looked at the one in the x-axis. This is the one in the y-axis. There's another pair in the z-axis. So in the z-axis, these are going to behave just like the ones in the y-axis. So we add them together. Now we're looking down from the top, and we see that it looks even more like the pi. So we get bonding and anti-bonding. Any questions? It's coming. There it is. Okay, so how do these molecular orbitals from the p orbitals, how are they in energy? Well, it's not actually the same for all of the elements, which is kind of a bummer. Boron, carbon, and nitrogen have a different order than oxygen, fluorine, and neon. But this is what's considered the typical ordering, where the sigma bonding is lowest, and then the pi bonding, and then the pi star, and then the sigma star. That's what's considered typical. So we got the sigmas on the outside, the highest and the lowest, and the pi's in the middle. So for boron, carbon, and nitrogen, it's going to have a different order. Let's look at the expected order first. So here we've got 2p orbitals, 3 from each, and when they interact, they're going to form a sigma bonding orbital and a sigma star anti-bonding orbital. They're also going to form pi orbitals, both bonding and anti-bonding. And so here, the pi orbitals are in the middle here, and the sigmas are on the outside. This is the one that's weird, and the thing that's different is that these two guys are switched. So here, the pi bonding is lower in energy than the sigma bonding, but these guys are the same. So boron, carbon, and nitrogen are the first letters in the phrase, be careful now. Those are the ones that do it weird. Be careful now. So they're going to do this, and the other elements are going to do that. And that's not something I'll try to trick you with on an exam. Can't vouch for mastering chemistry. This is an attempt to explain why it does that. Does anyone want to hear why? No, I don't think so. Okay. So here's boron, carbon, nitrogen, oxygen, fluorine, and neon, the diatomic homonuclear molecules. So for these three, their molecular orbital diagrams look the same. So we've got sigma 2s and sigma star 2s, and we've got the pi 2p and the sigma 2p, pi star 2p, and sigma star 2p. So boron, right? Boron's element number 5, it's in group 3a, it has 3 valence electrons. So then in this orbital diagram, we've got 3 times 2, save that one. 3 times 2 are 6 electrons. So 1, 2, 3, 4, 5, and here, this is Hund's rule. This guy's going to take his own orbital because he can. It's the same price. And then when we calculate the bond order, now we have 2 in this bonding orbital and 2 in those bonding orbitals. So that's a total of 4. And this is the anti-bonding orbital. Say 4 and write 2. That's helpful. So 4 minus 2 is 2, over 2 is 1. So this has a bond order of 1. For carbon, we're adding 2 more electrons. Where are those going? Well, now they're going to have to pair up in here. And this is a bonding orbital, and so that's going to make the bond order better, right? And then when we go to nitrogen, we're adding 2 more electrons, 1 from each, and that goes into sigma 2p, which reinforces the bond even more. And which one of these have you heard of? B2? C2? N2? Yeah, we've heard of N2. Well, N2 has a much higher bond order. So that's the be careful now. This is the typical ordering. And so here for oxygen, 12 electrons in here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The order is different here. So now we've got bonding orbitals, 2, 4, 6, 8. 8 electrons in bonding orbitals, and we've got 2 plus 2 is 4 in the anti-bonding orbitals, and so that gives us that bond order of 2. Not as stable as nitrogen. Well, and now we've learned that nitrogen actually forms a triple bond, right? And oxygen forms a double bond. So we would expect that the O2 is not, the bond is not as strong, because it's just a double bond instead of a triple bond. And then we can go to fluorine. We're adding 2 more electrons. These are going into the anti-bonding. And so those are going to work against it and make the bond order lower, but it's still positive. And F2 is another one of the diatomic elements. When we get to neon, we're adding 2 more electrons into the anti-bonding, and now We have an equal number in bonding and antibonding, and so there's no reason for this bond to form, and it doesn't. Any questions? The point of talking about this is not for you to become proficient at drawing molecular orbital diagrams. It's for you to understand the big idea of it, that electrons in bonds can be delocalized and spread out over the whole molecule. And if we are okay with that, then we can just sail on and never think about it again. So we know from experiments that oxygen is paramagnetic. It's attracted to a magnetic field.
When liquid nitrogen is poured onto a magnet, the magnetic field does not affect the liquid. When we pour liquid oxygen onto a magnet, however, it is held by the magnet because oxygen molecules are paramagnetic. Paramagnetic substances have unpaired electrons.
Now, weird. Why would, it looks like water, right? Why would water just stick in the magnet? Because it's not water. It was liquid oxygen and liquid nitrogen. So, paramagnetism is a result of unpaired electrons, right? Well, if we look at the Lewis model, here's the Lewis structure for oxygen. Do you see any unpaired electrons? We have some lone pairs and we have bonding pairs, but they're all pairs, right? So Lewis model says this should be diamagnetic. It shouldn't stick in the magnet, but it does. Here's the valence bond version. So here we have we have this sigma bond here and pi bond up here, but again, there aren't any unpaired electrons. So neither of these gives us the correct result for is oxygen paramagnetic. This is the molecular orbital diagram for oxygen, O2. And there we have two unpaired electrons. So this theory, which is much harder to deal with, harder to understand, harder to manage, but it correctly predicts more things. And that's why we kind of have to mention it. Okay? Okay, so let's see. This is the kind of a question that you could have on an exam, except I'll give you the diagram to fill in. Okay? So note to self, just put the stupid diagram in here so you don't have to draw it every time. So that's sigma 2s star, and this is sigma 2s. And then nitrogen is the be careful now, so it's kind of backwards. So it's got its pi 2p down here, and then it's sigma 2p, and then it's got pi, star 2p, and sigma star 2p. We really don't need to have the atomic orbitals on this side with all the lines coming in. What we need to know is how many valence electrons does N2 plus have? Well, there's two nitrogens, and they each have 5 electrons, right? And the positive charge means it lost one. So there's 9 electrons. So we're going to put 9 electrons into this funny diagram using the same rules we used for regular orbital diagrams. 1, 2, 3, 4, 5, 6, 7, 8. They're going to take their own until they have to pair up. 9. So do we expect this bond to be stronger or weaker than in an N2 molecule? Well, the N2 molecule would have another electron here. It would have more bonding electrons than anti-bonding, right? So we would expect that N2 plus is going to be weaker. Is it paramagnetic or diamagnetic? It's paramagnetic. Remember, diamagnetic, di means 2, 2 by 2, like the animals going into Noah's Ark. Here we've got an electron that doesn't have its friend. So this is paramagnetic. So that would be attracted to a magnetic field. But N2, when we put another electron in there, that's diamagnetic and it's not. And we saw that in the video. Any questions? So for an exam question, you would be given the correct molecular orbital diagram. You would be given some diatomic molecules or ions, and you could be asked about magnetism, paramagnetic, diamagnetic. You could be asked about bond order. Okay, here's no again. So this is heteronuclear. So then things really start to get kind of interesting. So here oxygen is more electronegative than nitrogen, and so its atomic orbitals are lower in energy than nitrogen's. And so then the contributions to the molecular orbitals are uneven. And if we look at HF, fluorine is so electronegative that its 2p orbitals are lower in energy than hydrogen's 1s orbital. And so then you end up with some wonky thing like this. And really all this tells us is we really don't want to look at heteronuclear molecules. But this is something we could do. Determine the bond order and is it paramagnetic or diamagnetic for FO minus. So here we would, unless told otherwise, we would just assume that we had nothing too crazy going on. We've got sigma 2s and sigma star 2s. And this is not the be careful now. This is the regular. And so the sigma 2p is down here, and the pi 2p, and this pi star 2p, and the sigma star 2p. So that would be given to you. FO minus. How many valence electrons? How many does fluorine have? 7. And how many does oxygen have? What group is it in? Oxygen has 6 valence electrons, right? And a negative charge means I have to add 1 more electron. So plus 1. So 14 electrons. This is the same as the first step in writing a Lewis structure. Figure out how many valence electrons. It's the group number. The trickiest part is if you have a charge, remembering that negative means you add and positive means you subtract. So 14 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. What's the bond order? This is bonding, this is bonding, this is bonding. Antibonding and antibonding. So in the bonding orbitals, 2, 4, 6, 8 electrons. In the antibonding orbitals, 2, 4, 6. 8 minus 6 is 2 over 2 is, so the bond order is 1. Is this paramagnetic or diamagnetic? Diamagnetic, because these electrons are all paired up like Noah's Ark animals, right? So it's diamagnetic. There'll be one question like that on exam 4. 1. We talked about ozone and the resonance structures for ozone. Well, the Lewis model can't handle it. Turns out the valence bond model can't handle it either. So we've already talked about that. In the valence bond model, we're going to end up with something like this. We have to put the double bond between these two or those two. There's nothing else we can do. In molecular orbital theory, though, those orbitals can be delocalized over the entire molecule, and so we can have pi molecular orbitals that are distributed over the entire molecule. And now we get a model that gives us what we know to be true, that these bonds are equal. They're equal in strength and length. So molecular orbital theory explains ozone. This is something that's important in organic chemistry. This is a molecule called benzene. It's got 6 carbons in a ring, and each of them has a hydrogen bonded to it. And there are 2 resonance structures in the Lewis model. So you have alternating double and single bonds around here, and the other structure is with the bonds in the other places. So what it actually is a combination of those 2, which Lewis theory can't handle. Valence bond theory can't handle either. But this is the molecular orbital theory model for that. And now we see that we can handle the electrons from those double bonds being spread out equally across the entire molecule. And so this is where they get that resonance stabilization. It's because the electrons are actually delocalized over the entire molecule. Any questions?